Lesson 1 will provide an introduction to the features of the 802.11 application framework. You will also learn how to run the system to stream real-time data over the air. In Section A, we will specifically discuss what an application framework is in LAVI communications. The NI software-defined radio platform provides software and hardware for prototyping. The software is LAVI Communications, which is a feature-rich IDE for programming on processors and FPGAs. The hardware is either the USAR Rio, which is a standalone software-defined radio, or PXI chassis with a Flex Rio FPGA card and an RF front end to provide more measurement-grade RF. The application framework specifically can be optionally purchased in addition to LAVI communications. These implement standard protocols. Specifically today, we will be discussing the 802.11 application framework for prototyping wireless LAN networks based on the IEEE 802.11 standard, but there are also application frameworks for LTE and for massive MIMO. On top of the application frameworks, free of charge are application examples, such as those integrating NS3 with LTE or LTE and Wi-Fi coexistence. An application framework is specifically here to provide a reference implementation of common wireless standards. The key tenets of the NI application frameworks are access to the source code, modular and easily modifiable designs, and a ready-to-run data streaming example. These provide you with a starting point for the implementation and validation of your new algorithms, systems, and testbeds in a real-time, over-the-air implementation. In terms of some examples of how you could leverage the 802.11 application framework for prototyping, you could perform experiments with 802.11 AX physical layer candidate modifications, explore better distributed MAC protocols, prototype better receiver algorithms such as synchronization or channel estimation or equalization, and look into LTE and Wi-Fi coexistence research in combination with NI's LTE application framework. In Section B, we will discuss at a high level which 802.11 features are available, how the system is designed, and what are the options to operate it. The 802.11 application framework enables over-the-air transmission out of the box. It also provides the ability to communicate between multiple nodes or use one device in loopback. It provides a real-time capable physical layer with features including synchronization, modulation and demodulation, channel encoding and decoding. And finally, there's a lower MAC, which includes features such as handling multi-node addressing, CRC, and frame type check, in addition to ACK generation conforming to 16 microsecond CIFS timing. The implementation of the MAC layer has been separated from that of the PHY for the ease of prototyping and modularity. This is the simplified block diagram of how the aforementioned features get implemented. This system includes three main components: the host running on the CPU, the FPGA code, and the RF hardware. The host primarily implements the graphic user interface, which allows you to control various parameters and also display data coming out from the application framework, such as constellation plots or throughput. The host also provides a UDP interface from which you can stream data to or from. The FPGA implements the computationally heavy operations such as decoding and the IFFTs, in addition to things like impairments correction. We will cover all of these blocks in more detail later in the training. The RF hardware provides the digital to analog conversion and the analog to digital conversion, in addition to the RF up conversion and the RF down conversion. In this system, the host will usually be a PC or laptop, while the target will either be the USAR Rio or the Flex Rio with adapter module as mentioned. The whole system is actually running in real time. In other words, we are not generating recorded RF signals, but the whole physical layer is running in real time on the FPGA. This is a view of the system design with the signal and data fields explicitly separated. In the host, the required parameters are configured, such as the modulation encoding scheme, or MCS. These will then be sent to the FPGA. In the FPGA transmit loop, the signal field will be created, and then the data field will be encoded based on the given MCS. In the FPGA receive loop, the signal fields should be read first, and then the data field will be decoded. The decoded data will then be sent to the host. It is important to note that control is applied for the same packet. All in all, this is what the complete picture looks like. The transmitter and the receiver are executed on a Kintex 7 FPGA on the USRP Rio or Flex Rio device. You have a data source that can provide things like video over UDP to the host. That'll get streamed to the transmitter on the host, and then the 802.11 packets will get transmitted over the air to the receiver side. The receiver physical layer will happen on the FPGA. That data will get transmitted back up to the host, and then the data can go through UDP to your actual final data sync. Section C, running the system. In this section, you will learn how to run the framework and how to use it for data streaming. Specifically, there will be an activity and an exercise to allow you to be able to stream video with your own setup at home. In this activity, you will set up and run the 802.11 application framework. Specifically, you will learn how to set up the hardware, check the hardware manager, create a project instance of the framework, run the framework, and change parameters. Step 1 is to set up the hardware. First, connect the RF ports of the USRP Rio. You have two options. You can either use an SMA cable and a 30 dB attenuator. In the image on the right, the cable would be connected to A and to the attenuator at B, and then the attenuator would finally be connected to your receiver. You can alternatively use antennas. Next, connect the USRP Rio to your PXI chassis, desktop PC, or laptop. Finally, switch on the USRP Rio, and then afterwards switch on your PXI chassis, computer, or laptop. Note that the USRP Rio is a PCIe device, so it must be turned on before your PC or laptop. Step 2 is to check the hardware manager. In Navi Communications 2.0, there is an integrated hardware manager. If you are in the lobby, go to the hardware tab at the top. If you've connected your hardware properly, your USRP Rio or Flex Rio should show up as a device on the system with an alias. Option 2 as well is to check NI-MAX to ensure that the USRP Rio was detected correctly. Step 3 is to create a project instance. From the lobby again, go to the Projects tab at the top and scroll down until you see the Application Frameworks folder. Click into that, and then open the version of the 802.11 application framework that corresponds to the hardware that you have. In other words, if you have a USRP Rio, choose that project, or if you have a Flex Rio, choose that project. Step 4 is to actually run the host application. From the Files pane in the left, open up the 802.11 host.gvi. Check the Rio device in the upper right to ensure that it has the same alias as the device you are trying to communicate with. Step 3 is to select the device bandwidth just below that. This should correspond to the bandwidth of the USRP Rio hardware or Flex Rio hardware that you are using. Step 4 is the reference selection for your clock. Step 5 is the operation mode, whether you're doing loopback or a different system architecture. Step 6 is to check your transmit frequency. This configures the LO of your transmitter. And then step 7 is to press run by hitting the green run arrow in the upper left. Then you need to wait until the FPGA ready button on the upper right turns blue, which indicates that the FPGA image has been downloaded and flashed to the chip. Finally, activate the station and you should see your transmission and receiving start to happen. Once the system is running, you can change different parameters to look at the different behaviors in the application framework. The parameters at the top, highlighted in yellow, such as the transmit frequency and power level, take effect after restarting the station. In other words, if you want to change your LO, you can change it and then turn off the station and then turn on the station with the sliding button in the middle at the top. The parameters on the bottom left can be changed on the fly. In other words, you can change the subcarrier format and the MCS and whether or not you're transmitting an ACK while the system is currently running. The parameters in the upper right, specifically the hardware that you're targeting and the device bandwidth and reference clock, take effect after restarting the whole VI. Now that your system is running, let's go through an exercise. This will help us understand how the different host settings affect the performance of the application framework. First, explore the encoding options. There is an MCS of 0 to 8 for 802.11a, or for 0 to 9 for 802.11ac. You can also play around with the subcarrier format with 20 MHz for 802.11a and the option for 20 or 40 MHz of real-time bandwidth for 802.11ac. When you change these, what happens? The next general thing to play around with are the data source and data sync options. For data source, look at PN data. Try out different PN data packet sizes and PN packets per second. Observe the changes in the throughput graph. Also, you can try changing the data source to manual. Trigger a single packet transmission by hitting Trigger TX. Observe the events on the Events tab and select which events to track by changing the Events to Track Boolean.